we got an action-packed video for you today. Just look at this list. In this video we shall explore for 3D vectors IJK notation and column vectors, the magnitude of a vector, the vector equation of a line, the point of intersection of two lines, the angle between two vectors, how to tell if two vectors are parallel or perpendicular, how to find the shortest distance from a point to a line, and how to find the point on the line for which the distance is shortest, aka the foot of the perpendicular. So what is IJK notation? Well, in 3 dimensions we have the x, y and z axes. Think about the point -5, -1, 6, where x is -5, y is -1 and z is 6. This point can be represented as a position vector in two ways. We can use IJK notation, in which I is 1 unit along the x-axis, j 1 unit along the y-axis, and k 1 unit along the z-axis. So -5, -1, 6 can be written as a position vector as -5i minus j plus 6k. Or we could use a column vector, as has been used for translations in the past, but with 3 numbers instead of 2. Moving on to magnitude, the magnitude of a vector is how long it is. Fortunately, we can apply Pythagoras' theorem in 3 dimensions as well as 2, so we use a squared plus b squared plus c squared is d squared. Let's find the magnitude of I plus 3j minus 2k. We square the numbers, add them, square root, and we get root 14. And similarly, for 3i minus j minus 4k, we get root 26. We've met Cartesian equations of lines in the past, i.e. with x and y, and you can even do them with z. But we are now going to look at the vector equation of a line. Yes, we are. The vector equation of a line is written in the form r equals a plus lambda b, where a is the known point on the line and b is the direction of the line. R is the general position vector of any point on the line for different values of lambda. Lambda is just a Greek letter. It is fun to use them from time to time. Yes, it is. Given 2 points on the line, we can find b by finding how to get from one point to the other, and we can also remove any common factors, which is nice. To find out how to get from a to b, we find b minus a. If, as is quite common, we are going to find 2 equations at the same time, we need to use a different variable. We use lambda for the first line and mu for the second. Mu is just another Greek letter. Lambda and mu are just LLM really. Find the vector equation of L1 through a, -5, -1, 6, and b, -7, -7, 10. So we need the direction of the line from a to b, which is b take a, which after removing the common factor of 2 gives us -1, -3, 2. And we are then free to choose any point on the line for a, so why not choose a? In IJK notation, this is r equals -5i minus j plus 6k plus lambda lots of -i minus 3j plus 2k, which can be rewritten as r equals -5 minus lambda i's plus -1 minus 3 lambda j's plus 6 plus 2 lambda k's. And I've done the same thing for the next question. Find the vector equation of L2 through C and D. I won't bore you with the details, you can pause the video and read them for yourself. Parallel vectors. We all know what parallel means, and in 2 dimensions we know that 2 non-parallel lines will always intersect, lines being infinitely long. Not talking about line segments, okay? But in 3 dimensions this is not the case. Non-parallel lines don't have to intersect. They could miss. When you fold your arms or cross your legs, they aren't parallel, but neither do they intersect. Anyway, for 2 lines to intersect, there needs to be a value of lambda and of mu for which all of I, j and k are the same, that's all. We put the coefficients from each of the 2 equations of I, j and k equal and solve simultaneously, ensuring that the values of lambda and mu we find work in all 3 equations. Find the point of intersection of lines L1 and L2. So, I'm going to equate the i's, j's and k's. So for example, L1 has -5 minus lambda i's, and L2 has -12 plus 3 mu i's, which means I'm free to write -5 minus lambda equals -12 plus 3 mu. Although there are various ways of doing it, I've got to choose one, so I'm going to double the I equation and add it to the k equation, which leads to mu equals 3 and lambda equals -2. I've then substituted these values back into I, j and k to ensure they all work, not just because I happen to enjoy that type of thing, and they do all work. Each side of each equation is an x, y or z value for our coordinates, so they are -3, 5 and 2. Finished. Now we move on to the angle between 2 vectors. To find the angle, we can use a scalar product, which is a dot b equals mod a mod b cos theta. If we are finding the angle between 2 lines, then we need to use the direction of each one, the b bit in the brackets. To find a dot b, we multiply the I coefficients, the j coefficients and the k coefficients and add the results. The magnitudes of a and b are found as before. If cos theta is positive, then the angle is acute, whereas if cos theta is negative, then the angle is obtuse, but we can't just take the angle away from 180 degrees to find the acute angle. Got that? Good. Then we shall continue with an example. Find the angle between lines L1 and L2. Note that we use the bits in the brackets. So a dot b is minus 1 times 3, plus minus 3 times minus 1, plus 2 times minus 4, which is just minus 8. The magnitudes were worked out before, so the length of A is root 14, and the length of B is root 26. Cos theta is minus 0.419, from which theta is 115 degrees to the nearest whole number. If we want the acute angle, subtract that from 180 degrees, getting 65 degrees. Back to parallel vectors. Two vectors which are parallel are multiples of each other. So, for example, 6i plus 8j minus 4k and 9i plus 12j minus 6k are parallel because they are both multiples of 3i plus 4j minus 2k. Assuming that the directions have already been factorised, we can also tell if two lines are parallel if their b's are the same. And if they're not already factorised, what are you waiting for? Factorise them. To check if two vectors are perpendicular, we can use the scalar product. If theta is 90 degrees, then cos theta is 0, and therefore a dot b equals 0 as well. Again, to check if two lines are perpendicular, we need to use the directions, the b bit, of the lines. In our example, all we have to do is apply a dot b to the directions, and unsurprisingly, we get 0, which confirms that the lines are indeed perpendicular. And now we turn our attention to the shortest distance from a point to a line. Obviously, none of these diagrams on this slide shows the shortest distance from point A to the line L. Of course, the shortest route from point A to the line L is the line perpendicular to L. As a result, we can use trigonometry to find the shortest distance. If we know the coordinates or position vectors of Q and A, then we can find the length of the hypotenuse and the direction, QA. If we know the equation of line L, then we also know its direction. And if we know the directions of L and QA, then we can use the scalar product to find the angle between them. We then use trigonometry in the form of sin x equals O over h to find the length of the opposite, which is the shortest distance we require. Here is our example. I've managed to squeeze 8 steps out of this process. Step 1, find QR. Using our method from before, we do r minus q and get 4 minus 1 minus 1. Step 2, QA is a minus q, which is 24, 17, 25. Step 3, find the angle between QR and QA. Using the scalar product, we get 70.747. Step 4, use trigonometry to find the distance FA. The opposite is h sine theta, which is 36.4. And now we can find the foot of the perpendicular. Step 5, find the equation of line L and hence an expression for the coordinates of F. We use the direction QR for B and the point Q for the position vector A. So F is at 4 lambda minus 11, 1 minus lambda, 9 minus lambda, for some value of lambda we don't yet know. Step 6, find an expression for AF. For this we use the general expression we just found in step 5 and the coordinates of A. Step 7, apply the scalar product to QF and AF. We know that QF and AF are perpendicular, so we know that A dot B is 0. When we apply this formula, lambda equals 3. Step 8, substitute lambda equals 3 into the equation of this line. As I said a minute ago, F is at 4 lambda minus 11, 1 minus lambda, 9 minus lambda. For some value of lambda we don't yet know, except we do now know that lambda is 3. So the foot of the perpendicular is at 1 minus 2, 6. Thank you very much for watching.